Let us first talk about the restrictions that must be imposed in the VECM model. In the previous tutorial, we discussed the matrix pi, which contains the long-run coefficients and the adjustment parameters. It is important to note here that only the rank of this matrix pi is identified. The coefficients within this matrix are not identified. As a result, we must impose certain restrictions or constraints on the coefficients. Under the Johansen normalization approach, we restrict one of the long-run coefficients to 1. In our VECM example, we will restrict the coefficient beta 1 to 1. With this restriction, the model becomes just identified and we can estimate the other long-run coefficient beta 2 as well as the adjustment parameters alpha 1 and alpha 2. With Johansen normalization, our VECM equations will look like this. Here, you will notice the change in the cointegrating relationship. Since the coefficient beta 1 has been restricted to 1, we do not need to estimate it and we can simply specify the variable xt-1 on its own. All the other coefficients stay the same as before. Now these equations are identified and we can estimate the VECM model. In general, the number of restrictions depends on the number of long-run relationships or cointegrating vectors. In a VECM model, we have to impose R² number of restrictions to make the model identified. Here, R is the number of cointegrating vectors or long-run relationships determined using the Johansen test. In our example, we imposed one restriction because we had one cointegrating relationship in the model. Similarly, if we have a model with two cointegrating relationships, then we will have to introduce a total of 4 restrictions on the coefficients. The adjustment parameters alpha 1, alpha 2 and the cointegrating vector work together to affect the variables delta xt and delta zt. These variables show short-run changes in x and z because they are in the first difference form. Therefore, we can say that the adjustment parameters and cointegrating relationship affect the short-run changes in x and z. First, let us focus on understanding the cointegrating or long-run relationship. The cointegrating vector and the long-run variables are shown in this part of the equation. When the value of this long-run component is 0, the variables x and z are in their long-run equilibrium. This also means that there is no need for any short-run adjustments or corrections. We can also see this in the equations. When x and z are in equilibrium, the error correction component including adjustment parameters and long-run relationship will be overall 0, and it will not affect delta xt and delta zt. This makes sense because there is no disequilibrium that needs to be corrected. X and z are in long-run equilibrium and we don't want any changes or adjustment in x and z. On the other hand, x and z will be in short-run disequilibrium when this component is non-zero. Then, the error correction term including adjustment parameters and long-run relationship will also be non-zero. Therefore, we will see some adjustment in delta xt and delta zt in the short run to correct the disequilibrium. The short-run disequilibrium occurs when this component is non-zero. This means that this short-run error can either be above 0 and positive, or it can be below 0 and negative. When this component is greater than 0 or positive, we have a short-run disequilibrium where the value of variable x is above its long-run equilibrium. Equivalently, this also means that the variable z is below its long-run equilibrium. To correct this, we will need x to decrease and z to increase so they can converge to their long-run equilibrium. On the other hand, this component can be less than 0 or negative. In such a case, x is below its equilibrium and z is above its long-run equilibrium value. Then, we will need x to increase in the short run and z to decrease for convergence back to equilibrium. Let us move on to the adjustment parameters which play a crucial role in convergence back to equilibrium. The signs of the adjustment parameters determine the direction in which the short-run variables will adjust. Here, the sign can be positive or negative, which further determines the negative or positive effect of the overall error correction term. Moreover, the value of the adjustment parameters dictates how much of the disequilibrium will be corrected in the next time period. First, let us talk about the signs of these parameters. The correct signs of the adjustment parameters depend on the long-run coefficients beta-1 and beta-2. If the signs are not correct, the model will not be stable because the variables will diverge instead of converging back to equilibrium. First, let us consider alpha-1 parameter in the first equation of delta xt. The condition for convergence of variable x is given here. The derivative of delta x with respect to xt-1 must be negative. This means that the change in delta x due to xt-1 has to be negative. Remember that we restricted the coefficient beta-1 to 1, which is attached to xt-1. Therefore, this derivative is simply the coefficient alpha-1. To achieve convergence back to long-run equilibrium, this alpha-1 must be negative and significant. If alpha-1 is positive, variable x will diverge instead of converging to equilibrium. Moreover, if alpha-1 is insignificant, variable x will still not converge. This gives us a simple convergence condition in the case of variables whose long-run coefficient is restricted to 1. The adjustment parameter of its short-run equation must always be negative and significant. In the second equation for delta z, figuring out the correct sign of alpha-2 can be tricky because the long-run coefficient beta-2 is not restricted. It can be positive or negative, and the sign of alpha-2 will depend on whether beta-2 is positive or negative. The logic behind the condition for convergence is similar to the first equation. The derivative of delta z with respect to zt-1 must be negative. The only difference is that the coefficient beta-2 will have its own value. This derivative is equal to the product of alpha-2 and beta-2, and the convergence condition states that this product must be negative. Therefore, if beta-2 is negative, then alpha-2 must be positive and significant to achieve convergence of variable z towards equilibrium. On the other hand, if beta-2 is positive, then alpha-2 has to be negative and significant for z to converge. When interpreting VECM results, we reverse the sign of beta-2 to interpret the long-run relationship. It is important to note here that we do not reverse the sign of beta-2 when checking this condition. We have to use beta-2 as it appears in the cointegrating vector of the results. Along with the signs, the value of the adjustment parameters also plays an important role in convergence. Let us consider the adjustment parameter alpha-1 and different values that it can take. As mentioned earlier, alpha-1 has to be negative and significant. So we will consider only negative values as examples. Suppose alpha-1 lies somewhere between 0 and -1. This means that our variable x will converge because alpha-1 shows the proportion by which the disequilibrium is corrected in one time period. For example, if alpha-1 is -0.5, it means that 50% or half of the disequilibrium will be corrected in the next time period. Therefore, x will keep converging towards equilibrium with time. If alpha-1 is exactly -1, then all of the disequilibrium or 100% of the disequilibrium will be corrected in the next time period. We get interesting results when alpha-1 takes a value between -1 and -2 because this leads to an oscillatory type of convergence. Suppose alpha-1 is -1.5, which means that there will be a 150% correction. As a result, we will see an overcorrection and x will jump 50% past the equilibrium value. X will end up on the other side of equilibrium, but closer to equilibrium than before. This will give rise to an oscillating behavior in convergence. Finally, when alpha-1 is less than -2 or more negative than -2, x will diverge from equilibrium. We will see a massive overcorrection and x will shoot past equilibrium and end up even farther away than before. This way, it will keep on overcorrecting and diverging away. Thank you for watching, and I will see you in the next tutorial.